Okay, so in this section, we're going to be finding moments and center of mass. So we're going to be finding the center of mass of an object distributed along a line or a thin wire. Locate the center of mass of a thin plate. Use symmetry to help locate the centroid of a thin plate and apply the theorem of Pappus for volume. Now, I was telling the other class this, and I realized how bad it was. So if I want to balance this thing, I have to find the center of mass. Okay, so as you can see, the center of mass to balance this is in the center. If I tried to balance this thing anywhere else, it's going to fall. Okay, when I was a kid, we used to have a seesaw. Our parents used to take their kids to the playground, and there was always a seesaw, and the seesaw was so much fun. You and your friend would get on the seesaw. One person would sit here, one person would sit here. And if you two were roughly the same weight, you would go up and down and you would have an amazing seesaw experience. However, if your friend weighed a lot more than you, or you weighed a lot more than your friend, and you both sat in the same spot, it's going to be like this, and your seesaw experience is not going to be as wonderful. So the point is to try to figure out where's the center of mass based on the number of masses that may be along a particular line. So that's what we're going to look at, and then we're going to go into center of mass for other things. Okay, so moments and center of mass, here we go. All right, so this seesaw experience may look as such. And I really feel like I did that wrong. I need to, Which one is negative torque? It wants to rotate about the axis. So torque would be this way. And anything going up is negative. Okay, I got it. Okay. All right, so let's say right here at x equals 0, there's a mass. That's what this is called, the fulcrum. Okay, and there's a point mass M1 located at X1, and then there's a mass M2 located at X2, and then there's a mass M3 located at X3. Okay. So therefore, there's a force F1, which equals M1G1. So that is the force that wants that mass to be held down. That's the force due to gravity. Mass times acceleration, gravity is acceleration. This one has a force F2, and it is equal to M2G. And this one has a force F3, and it is equal to M3G. Okay, so now I know the force, and so there's torque that wants this thing to rotate. All right, so each force wants to turn the axis about the origin. Okay, so the torque is the turning effect. And so it is a signed value. It is mi times xi. So it depends on the mass of the object and how far it is from the origin, which is why if one friend is bigger than the other, they may need to make an adjustment of their distance away from the axis so that they can, well, the origin, so that they can actually balance, okay? Oh, I forgot my G. All right, so this is the force times the distance. What is force times distance? Anybody know? Anybody know what force times distance is?
Isn't it torque?
It's torque, but it's also another word.
Work.
Moment.
I think I heard it. Say it again.
Work.
It is work. Okay, that's right. All right, so the system torque well, we compute that by summing them all up. So that's the sum, I equal 1, and in this case, we have 3 of our mi g times xi. So we're going to get m1 g x1 plus m2 g x2 plus m3 g x3. All right, so therefore I can pull the G out and get M1 X1 plus M2 X2 plus M3 X3. And I'm going to call this thing the moment about the origin. Okay. Okay, so the moment about the origin in general is to sum up all the masses times their distance, their signed distance away from the origin. Okay. So our goal is to literally figure out where we can place the fulcrum with the masses as they are so that we can balance the system. So this is our goal. So here's our goal. All right, so let's look at this. So here, I'm going to draw another picture, but this time I don't know, I know where the origin is, but I don't know where to put the fulcrum. So let's draw a picture here. And this is my origin. And then here's M1, X1. Here is M2, X2. Here is M3, X3. And I'm going to place my fulcrum right there. Okay. Okay, so the torque of a mass MK about X bar. Well, what is X bar? X bar is going to be the location of this. So if I want to find now, before we found the torque about the origin, now I want to find the torque about X bar. So for any particular XK, I'm going to take the distance XK, subtract the point that I want to be where I'm going to balance it, times its mass, and then times the gravity. I'm going to say one last thing and then I'm going to stop. So this is the sign difference. I don't want to be too far ahead of the other section. So that's the sign difference. And then over here, this is the downward force. Okay. So on Monday, we will finish this. Let me just say one thing. For a balance, and the sum of the torques will equal 0. Okay, we're going to stop here.